Hello dear students. In this today's lecture we will discuss about the various thermodynamic parameters such as entropy, pressure, specific heat, Gibbs free energy, Helmholtz free energy, and we will all derive all these relations. So let us start our lecture. In the previous lecture, as you are aware that we have derived the probability function, so that is PR, which is equal to NR over capital N, so that is exponential of minus B into ER over summation of R, which varies from 0 to infinity, exponential of minus BR. And this denominator term, that is generally known as the partition function, and it is generally derived or defined with the term Z, or in some books, so this is generally denoted with the notation Qn. So you can use this function, partition function, as with Qn or with Z, so it's up to you. So apart from that, we have also derived the energy function, that is the summation of n r, which varies from 0 to infinity, into e raised to power minus beta into er over summation of minus b into er. And from that we have derived the average energy per ensemble, so that is equal to summation of ER into PR, and we have derived the relation between this probability function and this energy function. So this PR, so let us say this is our equation number 1 and this is our equation number 2. So we can rewrite this equation 1, rewrite equation 1 and 2 something like this. So PR, probability function, so that is exponential of minus BR over summation of e raised to power minus b into ER. So I can write it something like that, minus 1 over beta. So if I take the derivative with respect to ER of the term log of this partition function. So when I solve this differentiation and I get this same equation, so this is our equation number 1 as it is, and similarly we can write this average energy per ensemble something like summation of e raised to power minus b into ER over summation of e raised to power minus b into ER. So this I can rewrite as minus curly by curly of beta log of this partition function, summation of e raised to power minus of BR. So if I take the derivative with respect to beta of this logarithmic value of this partition function, so I get these same results. So using these equation 1 and 2, we can find out the various thermodynamic parameters. So first of all, we will find out the Helmholtz free energy. So these two equations, they becomes the recipe for extracting the information, so from this microscopic properties. So let us now introduce a new quantity. So if I introduced a new thermodynamic parameter, that is A, which is equal to minus 1 over beta log of partition function. So if I consider this as the equation number 3, so where A, so our assumed parameter, it is a function of beta, and it is also dependent upon the spectrum of energy eigenvalues ER. So if I move this beta to the left hand side, so this becomes a into beta, so that is minus log of summation of exponential of minus beta into ER. Now if I taking the differentiation of this equation, so first with respect to beta and then with respect to ER, because it is dependent upon this beta and ER, so I can rewrite this equation, the derivative of this AB. So this is something like minus curly by curly of beta log of summation exponential of minus B into ER into dB minus summation of curly by curly of ER log of summation e raised to power minus B into ER into DER. So this is the equation which becomes, now this two equations, our equation number 1 and 2 I will rewrite here. So our first equation, that is PR, which is equal to minus curly by curly of ER into beta. So if I move this beta to the right hand side, so this is logarithmic value of summation e raised to power minus beta into ER. And similarly our equation number 2, that is the average energy per ensemble, which is minus curly by curly beta logarithmic value of this partition function. So these are the two derivative equation which we have found here in our this equation. So putting the value of this derivative in these equation, so this equation becomes derivative of a into beta, that is equal to u into dB plus summation of beta into PR into DER. So this is what we get. So we can rewrite this equation as U into dB. So don't get confused with the internal energy. So this is the average energy. So I will write it here. Average energy. So this becomes beta of summation R from 0 to infinity. So this probability, so whose value is the energy eigenvalue of nr over capital N or small n, you can write it as this one. So this is our equation number 4. Now taking the derivative of this b into u, so derivative of b into u, so this I can write as b comes outside, derivative of u plus u comes outside and derivative of beta. So suppose this is our equation number 5. So subtracting this equation 5 from 4, subtract equation 5 from 4, so what we get is d du minus d of AB, so that is equal to BDU plus UDB minus beta over n summation of NR into DER. So this I can write as BU minus AB, so that is equal to BDU minus of, so here there is one more term, that is UDB minus, so you can see, so there it is, UDB is also there, so I will write it as minus of UDB. So they get cancelled out and what we are left with is BDU minus beta over n into summation of eigenvalue of NR into DER. So this I can write as taking B as common, U minus A, that is equal to taking beta as common, du minus 1 over n summation of nr into der. Now this equation, it has quite importance in this thermodynamics. So let us say this is our equation number 6. Now if we assume that there is a mechanism with which energy levels they can be altered, so that all the systems they are affected in the same way. So in this equation number 6, the quantity, this summation of, so I will use different pen, so let us write it in a new page. So our equation number 6 which we have derived is d b u minus a, that is equal to beta du minus 1 over n, or you can write it as capital N summation of nr into der. So this is our equation number 6. Now in this equation, the term, so let me change the color. So this term summation of nr into der, so this denotes the work done by external agency in lifting the system of ensembles from energy Er to some finite energy Er plus der. So this equation, it is representing the quantity summation of nr into der denotes work done by some external agency in lifting the system of ensembles from Er to some slightly change in energy Er plus der. And if we put a negative sign, so in front of this equation, and the negative of this equation, so that is work done on the external agency. So if this is the positive sign, so what does it mean? It means that from the first law of thermodynamics, so it is work done by the agency on this system, and since here it is a negative sign, so this negative sign, it represents the work done on the external agency by this system. So negative of this summation nr into der, so this represents work done on the external agency. So our external agency is that our heat reservoir by the systems of ensemble. And this, if we divide this with the whole total number of systems which are present in the ensemble, so this is the average work done by one system. So this whole notation, that is the whole this notation, so this is represented with the average work done by one system. And du, so this du, that is representing the average energy increase per system of ensemble. So this whole bracketed term, So that is this Bracter term, that is this whole Bracter term. So this represented the average amount of heat transferred from heat reservoir into the ensemble. So this is purely the same equation du minus dW, so that is equal to dq. So that is the first law of thermodynamics. So this whole equation, it is following the same equation as that of first law of thermodynamics. So in this equation, so we know that beta, it is inversely proportional to temperature. So this we generally write it as 1 over kT, where k is the Boltzmann constant and our a value, so it is minus 1 over beta log of summation exponential of minus b into er. So this Bracter term, that is we have already derived that this is known as the partition function. So of n system, so if we are talking about the n system within the ensemble, then we generally represent this partition function as Qn Vt. So where Qn Vt, that is the partition function, which is summation of exponential of minus b into r from r1 to infinity. And on the left hand side, the quantity beta u minus a, so that is left hand side of the equation number c, so that is being equivalent to the entropy of system. So this we generally represent it as s over k, and putting the value of this beta, so u minus a over kt, that is equal to s over k. So this get cancelled, and from that we derive this equation ts, that is equal to u minus a, and a, that is u minus ts, where a is known as the Helmholtz free energy, and u is generally considered as the internal energy or the average energy of the system. So from this Helmholtz free energy, we can derive out the various thermodynamic properties of this canonical ensemble. So let us consider this equation as the equation number 7, and we will use this equation in order to find out the other thermodynamic parameters. So A, it comes out to be U minus Ts. So if I take the derivative of this equation, so this becomes du minus t into ds minus s into dt, and we have already derived the equation of du, so that is in our unit number 1. So while solving the classical ideal gas problem, so the change in internal energy, so this comes out to be TDS minus PdV plus mu into dN. So let us say this is equation number 8. Now putting the value of this du in this equation, so dA becomes TDS minus PdV plus mu dN minus TDS minus S dt. So this TDS and TDS get cancelled. So dA comes out to be minus of S dt minus PdV plus mu into dN. So this is the relation of A with the entropy. So let us say this is equation number 9. Now using this equation, so we can find out the value of entropy. So entropy we know, so using this equation, so if I take the derivative of this dA with respect to dt, so I can find out the value of this entropy. So S comes out to be minus of curly A by curly T as constant N and V. So A, we have already derived the value of this Helmholtz free energy, that is equal to minus of kT log of partition function Qn. So putting the value of this A in this equation, so our entropy value, so it comes out to be plus of K curly by curly T. So it is T into log of Qn at constant N and V. So this is the entropy value, and we can further solve it. So let us say this is our equation number 10. So similarly, you can also find out the various other thermodynamic parameters such as pressure, chemical potential. So by taking the derivative of this dA, if I take the derivative of this Helmholtz energy with respect to volume, and from that I can calculate the pressure value, and if I take the derivative of this equation with dN, and from that I can calculate this chemical potential. So pressure equation, I can write it as minus curly A by curly T. So that is at constant temperature and pressure. So putting the value of A, so pressure equation, it comes out to be kT curly by curly of V log of Qn. So this is, let us say, our equation number 11. And similarly, you can also derive the equation of mu. So mu is the chemical potential. So mu, that comes out to be plus curly A of curly T at constant volume and temperature, and mu, it comes out to be minus of kT curly by curly of N log of Qn at constant volume and temperature. So this is our equation number 12. Now we can further rewrite the value of U, that is the internal energy. So internal energy, which is equal to A plus Ts. So putting the value of entropy, I can write it this equation as A minus T curly by curly A over curly T, and putting the value of this A and T, this equation write as minus kT log of Qn plus T k curly A by curly T, we know that is equal to curly by curly T of log of Qn. So when I solve this, so this comes out to be minus kT log of Qn plus kT comes out to be constant. So taking the derivative one time with respect to t and second time with respect to log of Qn, because this partition function, it is also a function of beta. So the partition function, it is minus b into ER, and this beta function, it is dependent upon temperature. So we also have to take this term within our derivative term. So this equation becomes T curly by curly T log of Qn plus log of Qn. So Kt log of Qn, so this equation get cancelled, one term is cancelled, and what we get is our internal energy, it comes out to be Kt square curly by curly T log of Qn. So in whatever form, so they can be asked to find out the value. So sometimes in the numericals or in MCQs, the value of U, it is given different, and you have to derive this value, and from that you have to choose the correct answer. So similarly I can rewrite this internal energy in some other notation, so which is dependent upon this beta term. Now we know that beta, that is equal to 1 over kt. So if I take the derivative of beta with respect to t, so this comes out to be minus 1 over kt square. So what does it mean? So it means that this kt square I can write it as minus curly t over curly b. So if I put the value of kt square in this equation, so I can write it as the internal energy, which is minus curly t by curly b or curly by curly t log of qn, and this comes out to be minus curly by curly beta of log of qn. So similarly you can drive the relation of this internal energy with respect to beta, or you can drive it with respect to temperature. So this is very important equation. So let us say this is our equation number 13. So from that you can also find out the specific heat. So at constant volume, so Cv, so that is dependent upon this internal energy curly U by curly T at constant N and V. So U we know it is equal to A minus Ts, so that is T curly A by curly of T. So this equation becomes curly A over curly T minus T curly square A over curly T square minus curly A by curly T. So Cv, so we can also write it as minus of T curly square A over curly T square. So and so you can derive various thermodynamic parameters. Now we have to establish a relation between this probability function PR and entropy. Now Gibbs free energy, so which is generally represented with G, that is equal to A plus PV, and putting the value of this pressure, that is minus curly A over curly V. So I can rewrite this equation. So this comes out to be n curly A over curly n into V T. So this gives free energy. So it is, this is a very important relation. It is dependent upon this chemical potential mu into n. And one equation, that is our pressure term, so that we have derived, so which comes out to be kt curly by curly v log of qn, and this we can write it as, so pressure we know that is minus curly a over curly v. So I can rewrite this equation. So this comes out to be minus curly v curly over curly v, and A is minus kt log of qn I can write it as summation of exponential of minus beta into er. Now taking the derivative with respect to v, so this p comes out to be, p is kt curly over curly v log of summation e raised to power minus b into er. So this I can rewrite something like 1 over summation of, so since er it is the function of v, so it comes out to be minus of beta into er curly over curly v summation of e raised to power minus beta into er. So this pressure term, so it comes out to be kt over summation e raised to power minus beta into er. So summation of e raised to power minus beta into er, and taking the further derivative of this term, so that is minus b into er. So this we can write it as minus kt into beta summation of curly over curly v into er over summation of e raised to power minus beta into er multiply by exponential of minus beta into er. So this pressure term, that we can write it as minus summation of curly over curly v er into e raised to power minus ber over summation of, so this kt and beta, they get cancelled with each other because beta is 1 over kt. So this comes out to be summation of exponential of minus beta into er. So this is our equation, minus summation of curly er over curly v. So this term exponential of minus ber over this partition function, so this is generally written as nr star over n. So that is our probability function. So this pdv, if I move this derivative of v to the left hand side, so this p into delta v, that is generally known as the work done on the external agency. So it comes out to be minus of summation curly nr star over n d into er. So this pdv, that is generally known as, because it is negative, so that means that it is the work done on external agency by the system of ensemble. So you have counter checked your derivation. So this is the same derivation which we have derived in our equation number 6. So I think now you will get more clear picture of this. So this is the same equation, that is which we have derived, that is equal to work done. This one. So this quantity P, which was introduced through this thermodynamic, so they now acquire this mechanical heating, and from this we can further derive the relation of entropy. So U, we know, that is equal to A plus Ts, and this we can write it as Ts, which is equal to U minus A, and S comes out to be U minus A over T, or if we divide these terms with K, S over K, that is equal to U minus A over KT, and A we know that is equal to minus KT of log of Qn. So this equation becomes S over K, that is equal to U minus of kt log of Qn over kt. So this comes out to be U over kt plus kt log of Qn over kt. So this kt get cancelled. So what we get is U into beta plus log of Qn, that is equal to S over K, and from that you can rewrite this entropy equation. So S over K, which we have derived, that is U into beta plus log of Qn. So this we can rewrite S over K, so where our average energy or internal energy per system of ensemble, so this is we generally written as ER into PR. because we have derived this relation of average energy into beta plus log of Qn, and we can rewrite this with the summation of PR, because the maximum probability of finding the particle in any system that can be equal to 1. So multiply this equation with the summation of PR, and we can rewrite this entropy equation as summation of beta into ER plus log of Q if I find this PR term common in both the above cases. So this is our new equation. Now PR we have already derived, that is exponential of minus BER over partition function. So taking log of this equation, so log of PR, this we can write it as log of exponential of minus PE into R minus log of summation of e raised to power minus beta into ER. So this log of PR, that is equal to minus B into ER minus log of Qn. So if I keep this minus sign to the left hand side, so this comes out to be beta ER plus log of Q. So this is the same equation, beta ER plus log of Q. So this was the same equation. So I can rewrite this equation S over K, that is summation of PR into log of PR with a negative sign. So this is the interesting results, and this shows that our entropy of system, it is generally determined by this probability value PR. So we can also derive from this probability function, we can also find out the entropy values. Now this is very important results. Now if the system is in the ground state, so I will rewrite here the equation S over K, that is minus of summation of PR into log of PR. And if the system is in the ground state, so that is when all the particles within the system, they are completely at rest, so that is at a temperature of 0 Kelvin, then the probability PR, which is maximum for ground state, and this is equal to 0 for all other states. And then the value of this S over K in the ground state, so when PR is 1, so this comes out to be minus of summation of PR into log of PR, so that is for the ground state, and is equal to 0. So what does it mean? So in the ground state, so at 0 Kelvin temperature, the entropy is 0. So at ground state, the entropy is 0. So which is the same equation as the constant Nernst heat equation, and it is following the third law of thermodynamics. So what does it means? As the number of accessible states they increases more and more, P becomes non-zero and its log become more negative. So when the P becomes non-zero, so negative of log, so that is becomes more negative, and so negative and negative becomes the value of this entropy, which is equal to positive. So what does it mean? So as the temperature increases, the entropy value, it always increases. So this is very important relation in order to find out the entropy and how this is changing with respect to the probability density distribution function. So in our next lecture, so we will also tell you some alternative approach to find out this partition function, and then we will derive the classical ideal gas theorem or classical ideal gas problem using this canonical ensemble theory. So if you have any doubt, you can write your doubts in the comment section. So till then, goodbye, see you in the next lecture.